So welcome to the fourth lecture in our sequence on bonding. At the end of the last one, we had just started talking about resonance structures. And so now we're going to talk about resonance. When it came to adding the third bond to our sulfur dioxide compound, we had a choice. We could have put the double bond to either of the two oxygens and then filled in the electrons. And we get two slightly different structures as a result. The fact is, the atoms are all still the same. The electrons are simply arranged somewhat differently. And that's what we're talking about when we're talking about resonance structures. Resonance structures have exactly the same arrangement of atoms. They simply have different arrangement of electrons. And while in more advanced classes we'll run into the importance of resonance structures, they're basically outside the scope of this class and we don't have to worry about them. But it is something you have to keep in mind when you're doing Lewis dot structures where you have choices about putting double bonds in amongst the atoms, that yes, there are possibilities and you do get resonance structures. That is, you can end up with more than one structure that is equally correct. So let's consider another common compound, formaldehyde, CH2O. Who ends up in the center this time? Well, the carbon needs 4 bonds, the oxygen needs 2 bonds, the hydrogens each need 1 bond. So again, the carbon ends up in the middle, since it needs the most bonds, surrounded by the oxygens and the hydrogen. Do our heads need to chart? Carbon brings 4, would like 8. Oxygen brings 6, would like 8. Hydrogen brings 1, would like 2. Here again we see hydrogen is playing its own game. It's one of the exceptions in our octet rule. It wants to get to the closest noble gas, but the closest noble gas is helium, which only has 2 electrons. Hydrogen only wants 2 electrons. So the hydrogen brings 1, there's 2 of them, and it wants 2, and there's 2 of them. So we got, 8 and 8 and 4 is 20. We'd need 20 electrons for everybody to be happy. What we got is 4 and 6 and 2 is 12 electrons. So we're going to have to rearrange the 12 so they look like 20 electrons. 20 minus 12 divided by 2 is 4 bonds. So we need to put in 4 bonds. We put in 1 bond between the carbon and each of the hydrogens and the oxygen. That's only 3. And so we need to put in another double bond. In this case, we're not going to get resonance structures, because in fact there's only one reasonable place to put the double bond. The hydrogens only form single bonds. They're not capable of forming multiple bonds. So we can't put another bond between the carbon and the hydrogens. That means the double bond is going to absolutely have to go between the oxygen and the carbon. Put that double bond in, that's our 4 bonds. We simply need to fill in the electrons. The oxygen with a double bond for 4 needs 4 more electrons, so it gets 2 lone pairs. The hydrogen with a bond is satisfied. Hydrogen only wants 2 electrons. Do not put lone pairs around hydrogens in a Lewis dot structure. 1 bond is all the hydrogens need, so they're happy each with their single bond. And finally, the carbon with 2 single bonds to hydrogen is 4, and a double bond to oxygen is 4 more, and that's the 8 electrons for the carbon. So we've hung it together. Everybody has the right number of electrons. Last step is to count them up. The 2 carbon-hydrogen single bonds is 4 electrons. The double bond to oxygen is 4 more electrons, that's 8. And the 2 lone pairs on the oxygen is 12. That's the right number of electrons. And so we have our structure, Lewis dot structure for formaldehyde. The other compound you can make by combining oxygen and sulfur is sulfur trioxide, a sulfur and 3 oxygen atoms all hung together. Again, it is the sulfur which ends up in the center, surrounded by the oxygens, because we said the oxygens will prefer to pick on the least electronegative thing available, which again is going to be the sulfur. Do our has needs. Sulfur brings 6, would like 8. The oxygens each bring 6. There's 3 of them. They would each like 8. So 8 and 24 is 32. We need 32 electrons. We got 6 and 18 is 24 electrons. 32 minus 24 divided by 2 is we're going to need 4 bonds. First 3 hold it together. We're going to have to add another double bond. In this case, we're going to get resonance structures. We could put the double bond to each of the 3 oxygens, and it would be fine. Well, I'm only going to bother to use one of the resonance structures, but do keep in mind the double bond could have gone to any one of the 3 oxygens. So, an oxygen with a single bond to sulfur needs 6 more electrons. We have 1 on each side. The oxygen with a double bond only needs 4 more electrons to get to its 8. The sulfur in the middle, 2 single bonds is 4, the double bond is 4, so that's the sulfur's 8. So we've hung it together. Everybody has the right number of electrons around them. The last step in the Lewis dot structure is to count the electrons. The oxygen on the left has 6 electrons to itself and a share of 2. The oxygen on the right has 6 electrons to itself and a share of 2. That's 16 electrons. The oxygen to the north has a lone pair, has 2 lone pairs for 4, and a double bond to the sulfur is 4 more. That's 24 electrons. And we've already accounted for all the bonds around the sulfur. So that's our 24 electrons. So that would be one of the resonance structures for Lewis dot structures for sulfur dioxide. Now, I'm going to look at something a little different. Combining sulfur and oxygen, we can get something else that includes 1 sulfur and 3 oxygen atoms. In this case, it's an anion. It's a sulfite ion. It's a complex ion. And one of the things to consider is what holds the ions for each other is their coulombic attraction. But what holds the complex ions together? That is, the atoms that are actually bound together. And the answer, of course, is again covalent bonding. When you are talking about actually hanging the atoms together into one thing, you are talking covalent bonding. So what's holding the sulfide ion together is the exact same thing as is holding the sulfur trioxide together. So again, sulfur is going to be in the middle, surrounded by the oxygens, because the oxygens want to pick on the sulfur. Do our has and needs. Sulfur again brings 6, would like 8. The oxygens bring 6, would like 8. There's 3 of each of them. So 8 and 24 is 32. We need 32 electrons. 6 and 18 is 24 if it was a molecule. But it's not a molecule, it's an anion, which means it has extra electrons. In fact, it has 2 extra electrons, more than the molecule would. And so we don't have 24 electrons to play with, we have 26 electrons to play with. 32 minus 26 divided by 2, we need 3 bonds. Put in the 3 bonds and we have hung it together. And that's all the bonds we need. Now we can simply go ahead and fill in electrons. Each of the oxygens with a single bond needs 3 lone pairs to make up its 8. The sulfur in the middle with 3 single bonds is only 6, so it needs a lone pair as well. So we've hung it together. Everybody has the right number of electrons around it. The last step is to count the electrons. The oxygen, each of the oxygens has 6 to itself and a share of 2, so that's 24 electrons. And in addition to the 3 bonds, the sulfur has its own lone pair, so that's 26. And so we have a structure for the sulfite ion. And you'll notice that we put a bracket around it. Anytime you have an ion in a Lewis dot structure, you have to put brackets around it and indicate the charge on the ion. The molecules have the number of electrons you'd expect them to have, but the ions have a different number of electrons than the molecules would. If you go back and look at the sulfur trioxide we just did, you'll notice that it has a different structure, arrangement of electrons than the sulfite does. It's because it has a different number of electrons. And this is an important step in any Lewis dot structure. The reason you have to count the electrons as the last step is you have to make sure you have the right number of electrons. It's easy to draw Lewis dot structures, but if they don't have the right number of electrons in them, they're automatically wrong. The sulfur trioxide and the sulfite have different structures because they have different numbers of electrons. And so this is something to pay attention to. You always have to put brackets around ions in a Lewis dot structure. Has and needs works for molecules and anions. It also works for cations. Consider an ammonium ion. In this case, NH4+. Now obviously the nitrogen ends up in the middle because it needs bonds. Hydrogen is only capable of forming one bond, so hydrogen is never going to get to be in the middle of a Lewis dot structure. So the nitrogen is in the middle, surrounded by the 4 hydrogens. Do our has needs? Nitrogen brings 5, would like 8. Hydrogen brings 1. Remember, hydrogen only has 1 electron. Wants 2. It only has room for 2. There's 4 of them. 8 and 8 is 16. We'd need 16 electrons. 5 and 4 would be 9 electrons. If it was a molecule, but it's not a molecule, it's a cation. That means it has fewer electrons than a molecule would. And so we have to subtract 1 from our count. So we only have 8 electrons to play with. 16 minus 8 divided by 2 is 4. We put in the 4 bonds to hold the hydrogens to the nitrogen. And that's our structure. Each of the hydrogens with 1 bond has the right number of electrons, so don't put lone pairs on hydrogen. It only wants the 2. The nitrogen in the middle has 4 single bonds, and that's the nitrogen's 8. And so that 8 is the number of electrons we have, so we have to put the brackets around the cation, indicate it has a positive charge, and so we have a Lewis dot structure for ammonium. So that is how you do has and needs to come up with Lewis dot structures for molecules, cations, and anions. It works for all of them. There is a handout in Net Classroom if you want more instruction on doing has and needs. And now we have to start considering some other aspects of molecules, which is going to be for the next lecture.